The first thing with this proof is obviously to show what a cyclic quadrilateral is. If you draw a circle and you can draw a quadrilateral, a four-sided shape within that circle, then that is a cyclic quadrilateral. It should take a few moments just to convince yourself that not all quadrilaterals work this way. If you should, for example, draw a long, thin quadrilateral, it clearly wouldn't be able to be drawn such that all corners touch the circumference of a circle. So cyclic quadrilaterals are a subset of the set of quadrilaterals. So what we're trying to prove here is that opposite angles in the cyclic quadrilateral add up to 180. So for example, in this case, the angle at A plus the angle at C will add up to 180. This proof will rely mainly upon two things. First of all, it will rely upon the theorem that the angles at the centre are going to be twice the angles at the circumference, and you can look at that proof and go back and make sure you understand that one as well. But it's also going to rely upon the fact that in a full circle there are 360 degrees. So let's start and see how we work our way through this proof. The first thing we're going to do is to draw a couple of lines and add in a couple of angles that we are going to use as intermediate steps in our theorem. So we're going to draw lines across the quadrilateral and put in two angles, y and x. If we look at these two angles, we can see that x degrees is equal to 2 times the angle at C, and this is using the angles at the centre theorem. Similarly, we can say that angle y is equal to 2 times the angle at A. So now we have two equations, one for x and one for y. Now if we add these two equations together, we get x plus y is equal to 2 times the angle at C plus 2 times the angle at A. But here's the first bit we're going to use. X and y are equal to 360 degrees because they make up a full circle at the centre of the circle there. So we can use that fact to rearrange the equation to get 2 lots of C plus 2 lots of A is equal to 360 degrees. And if you follow that through, put the C and the A in brackets, we can see that C plus A is equal to 180 degrees. And that is what we wanted to prove. We wanted to prove the angles opposite each other in a cyclic quadrilateral add up to 180 degrees. It doesn't take a great deal of thought to see that if you turn the quadrilateral round you can do exactly the same thing for the angles D and B, but also we know that the angles in a quadrilateral all add up to 360 degrees, so by definition if 2 of them add up to 180, the other 2 must add up to 180 as well. This is quite a simple proof relying upon those two pieces of information, the angles at the centre theorem and the fact that in a full circle you have 360 degrees. Once you know those two things, it's fairly straightforward to work through this theorem and get the proof that you require.